Hi everyone. Welcome to our presentation. Today, we're excited to introduce SphereHead, stable 3D full-head synthesis with spherical triplane representation. Our method produces realistic head images rendered from full-range views by adopting a novel spherical triplane representation and a view-image consistency loss. While existing 3D aware GANs are able to generate realistic near-frontal face images, they are still incapable of synthesizing a full 3D head viewable from all angles, especially from the back view. PanoHead was the first 3D aware GAN focusing on full head synthesis and could generate a reasonable occipital region. However, its back view synthesis is very unstable and is often hindered by apparent fake face artifacts. In our paper, we analyze the causes of these artifacts in depth and provide corresponding solutions that allow our SphereHead model to eliminate them. As shown in this figure, there are two types of fake face artifacts. The first type is mirroring face artifacts, where the back face mirrors the same identity, expression, and accessories of the front face precisely. This occurs due to feature entanglement caused by the feature projection in the Cartesian coordinate system used in triplane or trigrid representations. For example, a point on the back of the head shares the same features on the XY plane with its symmetrical point on the frontal face. Because the supervision from the front view is much stronger than that from the back view, the frontal face features permeate into the back head region, resulting in these mirroring fake face artifacts. While PanoHead proposed a trigrid representation to alleviate this problem, it didn't solve it completely because the trigrid still shares a similar architecture and Cartesian coordinate system with the triplane. To address this problem at its root, we propose a spherical triplane representation, which is defined in the spherical coordinate system. Similar to how the triplane uses XY, YZ, and XZ planes to represent a 3D object, our spherical triplane uses theta phi, theta radius, and phi radius planes to represent a 3D object. The geometric properties of the sphere explicitly separate the features of each position on the head, thereby completely resolving the mirroring artifacts. However, in practice, these three planes are wrapped from square feature maps, which leads to artifacts at the polar regions and the seam region due to discontinuity of the theta plane at phi equal to positive and negative pi. Therefore, we further propose a dual spherical triplane to solve these artifacts. Specifically, we introduce an additional spherical triplane orthogonal to the existing one. That is, their polar axes are mutually perpendicular, and their seam openings are oriented in opposite directions, as shown in this figure. We then use a predefined weighting map to combine them together. As indicated in this figure, the weighting function W attains its maximum value at the center and gradually decreases to 0 at its edges, where the seams and poles are located. Due to this arrangement, the two planes wrap around each other akin to the two leathers of a baseball, each utilizing its smooth region to compensate for the problematic areas of the other. By implementing this strategy, we successfully eradicate the seam and polar artifacts. The second type of artifacts is multiple face artifacts, which arise because of imbalanced supervision. In this scenario, the fake back faces exhibit divergent attributes compared to the frontal faces, indicating that they are not the result of feature entanglement. The reason for these artifacts is imbalanced supervision in the dataset. During training, the generator quickly learns to generate high-quality facial attributes, but learns slowly to generate correct backhead attributes. Because in early training, the discriminator mainly judges based on visual quality rather than the consistency between the image and the view angle, the generator easily learns that generating facial attributes in the back view is an easier way to fool the discriminator. However, since facial attributes are artifacts in the back view, this keeps the back view synthesis at low quality. This means the discriminator's assessment of the back view remains in the early stages. Thus, it continues to evaluate images based on visual quality rather than their consistency with the view angle. Therefore, the training of the back view faces a dilemma, and the generator keeps producing multiple face artifacts in the back view. To break this dilemma, we propose a novel view-image consistency loss to force the discriminator to consider whether an image is consistent with its viewed. In practice, we construct negative pairs using real data to facilitate our view-image consistency loss. Specifically, for a batch of input data, real images and their corresponding camera parameters, we construct negative pairs by shuffling the camera parameters. Therefore, the view image consistency, VICO loss can be formulated accordingly. Thus, the discriminator can separate supervision by direction, protecting poorly supervised directions from the undue influence of those with strong supervision. As a result, the generator benefits from pure backview supervision, steadily enhancing the visual and content accuracy of the backview image synthesis. With the help of the spherical triplane representation and the view image consistency loss, our SphereHead is able to generate high-quality full-head images from all views. Here are more visualizations. Thank you for listening.